So these are some of the fit statistics that SAS gives you automatically. So sum of squares of error. Okay, and then if you divide by n, you get average squared error. And if you take a square root of that, you get root average squared error. This root stands for square root. And then MSE, so we discussed that just a minute ago. You take a square root of that, then you get root mean square error. And then if you take absolute value of the errors and average that, then you get mean absolute error. This is also known as MAD, mean absolute deviation. Then you can simply add up all the errors without squaring or without taking an absolute value and average them. Then you get average error. All of these measures are absolute measures. So you take the error and then you take an average, or you square it and take an average, or you take an absolute value and then an average, and so on. But there is one measure where the error is converted into a proportion. So you divide the error by the corresponding actual value. You take the absolute value of that ratio and average that, and it's usually represented as a percentage. So that's why you're multiplying by 100 here. This is called mean absolute percent error. And of course, this will be a value between 0 and 1, or 0 and 100%. And we can again use this to compare different models. And SAS gives a few more fit statistics which are not really very common. So these are described here, and I have a video about a little more explanation of this. I think you can take a look at that. All right, now let's look at the difference between evaluating predictive performance and goodness of fit. Okay, so when we do data analysis, we start with a data set, and the data set is already available to us, and then we fit a model using that data. Right? Now, how well the model that we develop corresponds with the data that we already have, so that's goodness of fit. How well it is fitting the data that we have already at hand. Okay. Sometimes that's our objective, in which case the goodness of fit between y and y hat is all we need. But data analytics typically is not about that. It is about predicting the future value of y. Okay. How well y hat fits the y that we already have in hand does not tell us very much about how that y hat will generalize for future. So how well the y hat, so just because y hat fits very well with the existing data, it doesn't mean that the y hat will generalize very well for the future data. So how do you evaluate the future predictive performance? Predictive, by definition, is about predicting something that has not already happened. So fit statistics are used to measure the goodness of fit, and they do not tell us much about the ability of the model to predict new cases. So what do we do? So the way in which data analytics handles that is, whenever you have a data set, what you would do is you would divide the data set into two parts. Typically, okay, we'll have a lot more to say about this a little later. So when you divide the data set into what is called train set and validate set. Now, train set is what you will use to fit the model. So the fitness statistics are all going to come from the train model, and you will use the y values of the train model and y hat values that the model gives, using only the train. Okay. Now, once you have the model, then you will apply the model to the validate set. The validate set is like pseudo new cases. Only thing is, since it is a data part of the data set that we have set aside, it acts as new cases, but we also know what the y values are for those new cases. Okay, so now you apply the model to this validation set, and compute the fit statistics and see how well the model that we developed using the trained data, okay, predicts the value of y in the validate data. So that's how we evaluate the predictive performance of the models. So here we will this is from SAS, and I have a video on how to develop this for Boston housing data set, and here you see all the different fit statistics that SAS generates. So this is from the trained data set, and this is from the validation data set. So you have average squared error, average error function, which is same as average squared error, and here let's see, maximum absolute error and mean square error. We talked about that. Okay, so you have trained set and the validation set. Okay, and then root mean squared error, summa squared error. So SAS will generate these fit statistics for both the trained set and the validation set, and the performance in the trained set tells us how well the model fits the trained data. And the validation summaries, these statistics that are calculated for validation set, they give us an idea about how the model will perform predicting new cases in the future. Now, when we look at prediction accuracy measures, sometimes the prediction accuracy measures are unduly influenced by outliers. Outliers are values that fall way beyond the normal set of values. Say, for example, if normal range of values is anywhere between 1,000 and 2,000, suppose if we have one or two values that are like 15,000, way above, or $3 or $4 or something, way below. So when such outliers are there in the data set, and if they are legitimate values, okay, sometimes typos will generate outliers, and if there are typos, then you correct them. But if they are legitimate values, then we have to use them in our analysis. So in such cases, there are several approaches that we can take. One is there are some data transformations that we can perform to bring the outliers closer to the main data set, or we can use measures, performance measures that are not unduly influenced by outliers. So they will be like median based measures, and we can use those for the purpose of comparison. And we can check whether there are these issues like outlier issues by plotting the histogram or box plots of the residuals. You take the residual meaning y minus y hat, the error terms. So the error terms, you plot the error terms, and if the error terms are completely random, so that means there is nothing much that can be done. The model that we have is probably the best model that we can get from the data set. But if the residuals show a pattern, then that means there is some more modeling opportunity left in the error. So we need to look for some other model, a different model, or different model parameters, tuning of models, and so on. So it is very important to plot the residuals or errors. Okay, you can use histograms with y hat on the x-axis and the residual errors on the y-axis. Okay, or you can just simply do a box plot of the errors. So plotting the prediction errors distribution, like in a histogram or box plot or scatter diagram with y hat on the x-axis, is very useful in measuring or in understanding whether the model has given us the best result that it can give. So here is an example of a residual histogram. So a histogram like this, looks quite nice, and it doesn't have. And if you look at the values, there are not a whole lot of extreme values. And here is a validation. This is a box plot of train and validation, and you see here. So this is our end of whiskers, and these points here show that there are outliers. So this means that there are some outliers in residuals and that needs further study.